Hello, welcome back. Hopefully the review assignment or the review video I gave you yesterday didn't just totally wear you out. I know it was quite a bit, everything I gave you yesterday. So today will be much easier. I'm going to go through half the problems on the assignment for you, and there's nothing else for me to talk about because I pretty well reviewed everything we've talked about so far. In the 30-minute video yesterday, that was either the most helpful or the most frustrating video that you've watched because it was everything that I've taught to this point. My goal in making that video was just to flash the images in front of your eyes really quick and just kind of quickly recap all the things that we've talked about with quantitative data, categorical data, independence, and histograms, box plots, all that good stuff. So anyway, we're just going to go, there's really nothing else for me to talk about today, so we're just going to go right into the assignment to make it quick and easy. Also, don't forget to study your practice test because tomorrow we're taking the actual quiz. So just procedures for the quiz. So just take it like you would take it at a quiz in class. Please be honest. So don't use your notes or your book. Just take the test. Make sure you write on the PDF. Edit the PDF, of course, so I can see your work. Also, I'll have you submit the answers, the multiple choice part, into Mastery Connect just to make it easier for me to be able to grade those. And then I will grade the free response by hand. And that'll be, after that, I'm also going to put in your grades for the homework that we've done so far so that we'll have some grades in PowerSchool. So anyway, and you guys will have until the end of the month, September 30th, to turn in the rest of your homework for this unit. Before we take the test, which is we plan on taking that on the 30th. So if you are behind, make sure you get caught up by then. The quiz will kind of give you an idea of how you're doing and how the grading is going and stuff like that. So by the time we take the test, you'll kind of know where you stand in the class. All right, so let's go ahead and get started. Number 28. Is your birth order related to your choice of major? A stats professor at a large university polled his students to find out what their majors were and what position they held in their family's birth order. The results are summarized in the table. So down here we have math, science, agriculture, humanities, or other, and then birth order. So first would be firstborn. So that would mean either they're an only child or they have no, or they're just born first. Second would be they're the second child, the third child, the fourth, or more. And then we also have the margins here and the margins here. So this is a contingency table because we're asking for each case, we're asking for two variables. Birth order and major, which is the blue thing here, birth order and major. The possible categories for birth order were broken down here, and then the possible categories for major are broken down here, and every person would fit somewhere within those two variables. And this is basically a contingency frequency chart here, and then the margins here are going to collapse it from where it's distributing across two variables to where it only looks at one variable. So the total over here would be the marginal distribution for the major, where we're no longer interested in breaking it down by birth order, but just all the majors, okay? And then on the bottom, that's kind of collapsing the second variable so that we're only interested in birth order, and we're not breaking it down. This is just birth order, not breaking it down contingent on their major. So anyway, that's what's going on with the contingency table. So we need to be able to answer these four questions. They are four different questions with four different answers. So even though it seems to be asking a similar thing, you got to make sure you read the wording very carefully. So what percent of oldest children are humanities students? So the first question we need to ask is who's the denominator? Who are we talking about? So of the oldest children. So how many do we have that were the oldest children? So out of the 113, what percent of those were humanities majors? So that would be 15 out of 113, which is going to give us a percentage of about 13%. Next question is what percent of the students, what percent of students are oldest children majoring in humanities? So our denominator now is of all the students. So of all the students, that's 223. That's now our denominator. So of the 223, what percent of those are oldest or only child humanities? Which would be 15 out of 223. So we have a different denominator this time, which would be 6.7%, about half of the last one. What percent of students are oldest or an only children? So now we're only interested in oldest or other children. So that's going to be one of our marginal distributions, which is going to be the 113. So, sorry, what percent of these students are oldest or only, okay, so 113 out of the total number of students, which is 223. So So that would be 113 out of 223, which is about half. So this is interesting. About half of the students are the oldest or have no siblings, which is pretty interesting. But what percent of humanities majors are the oldest children? So of the humanities majors, so that would be of the 43, 15 out of 43 are going to be humanities. So that's going to be 35%. Now these two percentages here are special. One of them is a conditional distribution and one of them is a marginal distribution. This is actually how we check for independence, which is kind of cool. So the marginal distribution says that the oldest children make up half. The first birth order 1 or whatever makes up 51% of all the students, but for humanities and firstborn only make up 35% of all the humanities majors. So the humanities majors are underrepresented among firstborns. So firstborns typically seem to major in other things instead of humanities, which is interesting. So that means that there is evidence of an association. So if we want to look for independence or evidence of association, we compare a marginal distribution, like the 51% are humanities majors, or 51% are born first, to the conditional distribution, which is of the humanities majors, what percent of those are firstborn, which is 35%. So anyway, kind of interesting there. Next one. Does being the oldest child seem to be independent of your decision to major in humanities? So another way you could look at this is looking at the marginal this way. So it looks like 19% of all of our students majored in humanities, so that's 43 out of 223, but 13% of firstborns majored in it, and again, it's lower than what we'd expect. We'd expect it to be 19 across the board. It's the same thing with the survival rates. Like on the Titanic, the average survival rate was 32%. So if they were independent across all the conditions, across all the classes, we would expect it to be 32%, but it wasn't. It was going up, right? So because these are not all the same percent, they're not all 19%, that means that there is an association between major and birth order. And the way we test that is by comparing a marginal distribution to a conditional. That's simple. What two types of graphs would help us visually compare the categorical data to determine if birth order is independent of major? So there are two that we use for categorical data. These are the only two types of graphs that we use for categorical data. Those are pie charts and segmented bar charts. No, we also use bar charts for categorical data. That's true. I'm sorry. But these are the two that help us visualize whether or not they're independent. And the reason for that is they break them up into proportions or percentages of the whole. So whatever category you're in, whether this was math and science, agriculture, humanities, or whatever, or if we broke it down by birth order, it would give us the percentage out of the whole, which would allow us to compare larger groups to smaller groups because both of them are going to be out of the entire whole. So if we graph these out, the percentages, the conditional distributions for either one going horizontally or vertically would give us the same information. As we graph them out, we'd see that they weren't the same, just like we saw with the Titanic. Alright, number 16. So I'm going to do all the odd problems with you, or the even problems, so then you can look at the back of the book, if you've gotten your book so far, so that you can figure out the answers and check your solutions to the odd problems. So the data from England and Wales notes for each town, whether it's south or north of Derby. Here are the summary statistics and comparative box plots for the two regions. I think if you read a problem before it somewhere, it'll explain what this data is even talking about, but this is like a second problem or whatever. So what's the overall mean mortality rate for the two regions? So we have the north region and the south region, which is graphed out in box or whisker plots, which is nice. And then here we have the summary of the mortality. So we got group north and south. Notice the counts are different. There's different sample sizes for the amount of data that we gathered for north and south. There was more in the north group than there was in the south group. We have the averages for the north and the average for the south. They want to know what's the total mean or total average mortality rate for the two regions. So we want to combine those two rates together. So you might be thinking the way that we would do this is that we would add them together. So 1631.59 plus 1388.85, and then divide them by 2. So that would just give us the average between the two. But that's not quite right. We actually have to do a weighted average or weighted arithmetic mean. It's kind of fancy words. And what that means is that these two are not going to be equally weighted because they have different sample sizes. So this would be just a regular average between the two, but because one of them is weighted more than the other one, the north group is going to be weighted more. It tells us that the actual weighted mean should be closer towards the north group, which is the higher number, than it is the south group, which is a smaller number, because the two are not weighted the same, right? So instead of 1510, it's actually going to be higher than that. But how much higher? Well, we have to know how to do weighted averages. Now what's kind of cool is I was never actually like taught weighted averages. I just kind of like figured out how we would like make the formula for it or whatever. So what you're going to end up doing is you're going to take the mean and multiply it by the sample size. And what that's going to do is going to give you the total mortality rates for all 34. Then we're going to add the same thing of the mean times the sample size for this one, which is also going to kind of weight it in proportion as well. You're going to take all the total mortality rates together and divide it by the total, which is the 34 plus the 27, which is 61, and that will give us back to the mean or the average weighted mortality rate, which is kind of cool. I hope you can see the difference between that and how the math works. It's kind of fun. I actually like stumbled upon that and just kind of made the formula. Then of course I looked it up, and I don't even think I knew it was called a weighted mean. I just thought, or weighted average, just thought, hey, that makes sense because you're weighting some things heavier than others, like in grading. And sure enough, I googled weighted mean, and weighted arithmetic mean is it's a thing, and this is the formula, so I got it right. So do you see evidence of difference between mortality rates? Yeah, I would say so, because if we look at the mean, it's significantly higher, but the mean might not be appropriate if it's not unimodal and symmetric. So even if we look at the median, which is kind of the more conservative measure of the center, which is what we would use for anything that's not unimodal and symmetric, is what I mean by that, even that one is higher as well. Also, if we look at the box plot, which kind of actually shows us more information because we got a 5-number summary from it, we can see that the north region is much higher mortality rates than the south region, and you can justify that by picking lots of things. You can just say the mean is higher. You can say that the top 75% of the north is higher than the bottom 75% of the south. Okay, so if we drew a line across there, that's pretty telling. Also, you can say the entire interquartile range is higher than the interquartile range of the south. That would give you typical behavior. We've discussed interquartile range would be appropriate. All right, number 20. In its traffic safety facts in 2005, National Highway Traffic Safety Administration reported that 6.3% of licensed drivers were between the ages of 15 and 20. Yet this group was behind the wheel in 15.9% of all fatal crashes. Compare the marginal distribution to the conditional distribution to explain the concept of independence. Does it appear to be an association between age and fatal crashes? So just thinking about that, if they make up 6.3% of all the drivers out there, that would be the marginal distribution. Like if we collapsed it across whatever the other variable was, I guess fatal crashes are not involved in fatal crashes, I don't know. So they make up 6.3% of all drivers, but they make up about 16% of all fatal crashes, which would be the conditional. So of all fatal crashes, what percent of those are these teenagers? And so because the conditional distribution is higher than the marginal distribution, higher than we would expect, that tells us there's definitely an association between the two. It's almost it's about 2.5 times higher than what we would expect, right? So in other words, their teenagers are involved in more than their fair share of fatal car wrecks. So if they were 6.3% of all the drivers out there, they're involved in 16% of all the fatal crashes, which is more than their fair share. Another thing that you might want to look at this is who's on the road more. So if teenagers were on the road more than just the amount of people the drivers are out there, then it might not actually look that bad. So kind of interesting if you think about it. And that's what's nice about statistics, is you can think how the data is being prepared to you, and you can actually critique it. And a lot of times you can kind of call BS on some things, like some other stats that people try to throw at you, which is fun. So have a critical mind and be able to start thinking about how people could be misleading you in the way they're presenting statistics to you. Like maybe this one, if teenagers were on the road more than the typical licensed driver. All right, 24. Roger Maris's 1961 home run record stood until Mark McGwire hit 70 in 19 98. Listed below are his home run totals for each season McGwire played. Also listed are Babe Ruth's home run totals. So we have both of those. No big deal. Find the 5-number summary for McGwire's career. So the way we're going to do this to find the 5-number summary is we need to put it in the calculator. So hopefully you have your calculator by now. If not, message me on Remind. And from 9 to 3, not from 11 to 12 or 1 to 2 because of my office hours, but any other time between then, message me and I'll get it to you. You can meet me up at the school. Alright, so find the 5-number summary. So what I'm going to do is go to the Stat button, hit Edit, and I'm going to put McGwire's in for the first list. Now I've actually already done it. It's not in order because I had to delete some, but anyway. So he's in list 1. So then I'm going to do Edit, Calculate, 1 variable stats, second 1 to do list 1, and then hit Calculate. And that's going to give me the mean and standard deviation, but I really want the 5-number summary, so I'm going to get that from the last 5 here, which is 3, 25.5, 36. Anyway, you can read it. It's also on the screen there. Okay. Next, we want to calculate the left and right fence to determine if any of his seasons appeared to be outliers. Well, he had several really small seasons, or seasons where he only had a few home runs, like 3, 9, 9. And so those might be outliers, and even when I graphed it out with a histogram, they look kind of like they're off by their own and possible outliers. So in order to do that, the left fence, we find 1.5 times the interquartile range. So to find the interquartile range, that's going to be 50.5 minus 25.5. Okay, then I multiply that times 1.5. And that's going to be 37.5. And then, so that's what this value is here. I'm going to subtract it from the first quartile. This value here, that's a 37.5. Subtract it from the first quartile. So visually, that's what's going on here. And it is going to give you negative 12. And of course, you can't have less than 0 home runs in a season, so there's no way we have any low outliers. And our minimum 3 is well above negative 12, right? Then we add it to our third quartile. Okay, so third quartile, that's what's going on here, which will give us 88. And his largest, or the maximum, was 70, which is within the fence. So within the left fence of negative 12, and the maximums within the right fence of 88. So there are no outliers for this data. And if we look at the modified box plot, you'll notice there's no outliers shown with any asterisks or any other dots. Alright, so make sure you know how to calculate left and right fence for the quiz. That'll be very important. McGwire played only 18 games at the end of his first big league season and missed major portions of some other seasons because of injuries to his back and knees. These seasons might not be representative of his abilities. They are marked with asterisks in the list above. Omit these values and make parallel box plots comparing his seasons with Babe Ruth. So I'm going to go into Stat Edit, and I'm going to delete those seasons, which I just put them on the end. So yeah, it's these seasons right here. So 3, 9, 9, 32, and 29. There is a small one of 22. It just wasn't a very good season for him. And then in list 2, I put them in alpha, or I put them in order, ascending order. That's why they look different than probably what you have. So then we want to make box plots. So to do that, I want to recalculate 1 variable stats. So this will be for McGwire, and then look at my 5-number summary. So the minimum is 22 for McGwire, the first quartile is 33, median is 42, third quartile is 58, and maximum is 70. I'm going to do the same thing for Babe Ruth. So second 2 for Babe Ruth, list 2. Look at the last 5 here. So minimum is also 22. First quartile is 35, which is higher. The median is 46, which is higher. The third quartile is lower, it's 54, and the maximum is 60. Okay, so those are called parallel box plots because they're on the same scale and they're right above each other, so it makes it easy to compare the two. Write a few sentences comparing the two sluggers. So, who had better seasons? So, the higher the maximum, the better seasons were from McGwire, but it looks like typically Babe Ruth had better seasons. He just didn't have like the higher numbers, if that makes sense. And the reason for that, I would say, is because his median is higher than McGwire's. So McGwire had a lot that were lower than Babe Ruth's. Another thing you can also say is about the overall spread. So the interquartile ranges are different. So McGuire has much more spread in the overall range and interquartile range. If we look from his high, his maximum is higher, they have the same minimum, but also the interquartile range, which is more important than range, of course, is going to be a bigger box than the interquartile range for Babe Ruth. So Babe Ruth was more consistent. He had typically had more home runs in the season, but McGuire had some seasons that were better than the best seasons of Babe Ruth. So he would have the record. Anyway, so you can describe that with just a few sentences, however you like. Create a side-by-side stem and leaf display. So to create that side-by-side stem and leaf display, you're going to want to sort your data in ascending order. So go to Stat Sort A for sort ascending, which is the second option, and then you can do list 1 by hitting second 1, and that's going to sort it. You can do just arrow up and then hit enter, and then you can do the same thing for list 2. It's kind of a shortcut. Anyway, so now they're both sorted in ascending order. I'm going to go to Stat and Edit, and then now this will make it a lot easier for you to fill in the stem and leaf plot. Make sure you know how to actually fill it in from the data instead of just copying what I do, but I wanted to make it look nice for you. So anyway, we would go 22, 32, so that would be for McGuire. So 22, 32, 33, 39, 39, 42, 49, 52, 58, 65, and 70. So make sure you know how to read a stem and leaf plot. This is called a back-to-back stem and leaf plot because obviously our stem is in the middle, and then we have leaves going in both directions, and they're back-to-back. So it's kind of cool. It makes it easy to compare. Anyway, so yeah, we'll answer the question here. What aspects of the distributions are apparent in the stem and leaf displays that are not clearly shown in box plots? So box plots are summaries. It's just a 5-number summary graphed out visually where our eyes are naturally drawn to the box, the interquartile range, because that's what's most important, but also the whiskers help us decide skewedness as well, and maximums and minimums. But when we look at the actual stem and leaf plot, back-to-back stem and leaf plot, it gives us the actual data and the actual shape of the distribution. We might be able to tell from the summary whether or not it's skewed, but you can see the actual shape, like if it was bimodal or multimodal or unimodal. We can see that from the actual data from the stem and leaf plot, or from a histogram as well, or a dot plot for that matter. Anyway, so what's apparent in a stem and leaf plot that you don't get from the summary over here? The actual shape of the distribution, which is whether or not it's unimodal, multimodal, anyway, that whole part. And we also can clearly see the actual data itself. It preserves the data values like 54, 54, 59. Instead of here, we know the max and the minimum, but all the and the quartiles, of course, but all the other data values in between it, like this mode and how they're all stacked up for Babe Ruth, you couldn't tell that from the box plot. Maybe you can see because the interquartile range is more narrow, there's not as much spread. You can see here it does kind of seem to be compiled for Babe Ruth, but more spread out for McGuire. We can see that kind of from the box plot, but those are just general shapes, not the mode. Like if it was bimodal, we wouldn't be able to tell that from the box plots. Hey, that's it, under 25 minutes. Awesome. So I will let you guys go. Make sure you study and you're ready for the quiz tomorrow, and I'll see you guys later. Have a good day.